today's video, we're going to be going over separation of variables and how they relate to the Laplace's equation. Okay, so to begin, what even is Laplace's equation? Okay, we're going to draw out what the formula looks like, and then I'm going to kind of explain what it actually means and why it's important. Equals 0. So we have the gradient squared acting on V, which is also known as potential or voltage, is equal to 0. Now, where do we even get this? This is only when there is zero charge, right? Zero charge density in whatever medium or whatever space that you're looking at. So if that seems super confusing, don't worry about it, go over it. So this actually comes from something called Poisson's equation. I hope I'm saying that right. Which is that it looks very similar. The Laplacian, or also known as the second derivative, the gradient squared of V is equal to rho over epsilon naught, with rho being the charge density. Right? So what this is saying is that you have this gradient squared on this potential. If you ever want to find the potential of a system, you would need to know the charge densities and the charges going throughout that system, and then obviously E naught is constant. And if you don't have any charge density, or if your charge density is 0 in whatever space you're in, whatever box you're in, then you're gonna just end up with Laplace's equation. And this is super useful when we need to figure out some equation for our V. So that's kind of the whole point, is to figure out some equation for our potential, right? Now, how we can do that is by starting general and then slowly reducing in order to get something that's actually quite specific to this kind of system. That seems abstract, don't worry about it, go over it. So how would we write something just general for V, right? Because we know it's a function. In this case, we're going to do it in Cartesian coordinates, and we want to manipulate it in such a way where we see if things cancel, if they stay the same, and whatnot. Okay, so how we're going to do that? Let's say we know that V, again we're working in Cartesian coordinates, is a function of x, is a function of y, and is in a function of z. Now we know that to be true. That takes into account all of space. Keep in mind this is electrostatics, so we're not really worried about time. So we have V of x, y, and z. I don't really like how that looks. I would rather actually write this as we have V is some function of x with respect to x, right? So we're going to call that x of x. In some classes, you might actually call this V subscript x. Essentially the same thing, right? Because V of x is a function of x. Okay. So there's a component that's only really concerned with the x direction for our potential or for our voltage, and then there's also going to be a component that is only concerned with, not plus, my bad, that is only concerned with the y direction, right? But there's still one missing, so we got to add that in. We also know that there must be some component only concerned with the z direction. All right, so that's looking a little nicer, looking like we can maybe do some work with this just because we're separating variables, that's the name, in the x, and the y, and the z. Okay, so you may not see, like, oh, they're together right now. Don't worry, we're getting to where they start getting separate. All right, so we have this equation, and we know what V is. So what I want to do is just plug it in. So let's just take this. Oh. So let's take our V and let's just plug it into there. Great. Let's write that out. So we're going to have nabla squared acting on V just wanted to plug that in. So we have v of x. We're going to have on x of x, y of y, and we're also going to have z of z in there. Keep in mind, this all is equal to 0. Right? So, drew it a little wonky, but you get the gist. So, how does this help us? Well, we're getting closer to eventually defining what our x of x is, y of y, z of z, and then kind of backpedaling into finding what our v is, right? Because again, this is our v. All right. Well, we can expand out one more thing in this equation. Can't expand out the 0, sadly. That'd be cool though. So we have nabla squared. Well, what's nabla? Hopefully, this is going to be an aside. If you already know what nabla is, you already know how to get nabla squared. I'll put a timestamp in the video so you can go there. But if you don't, this might be useful. Okay. So, nabla. Alright. Nabla, not squared, is equal to this change partial derivative with x, right? So partial derivative of x with respect to the x direction. So that's what this x hat means. Plus this, again, this nabla is like, it's just a tool. You can think about it conceptually with how much does something change with this x hat direction, how much does it change with the y hat, how much does it change with the z hat. But at the end of the day, for physics, it's a tool. Okay. Y hat. So we have the partial with respect to y hat, with respect to y in the y hat direction, plus the partial of z with respect to the z hat direction. Okay, so this is nabla, right? But what about nabla squared? All right, well, how we square something? If it's a vector, that's what this little line means. This little arrow right here means it's a vector. Is we dot it with itself, right? So if you want to find a vector velocity squared, you'd have to do v dot v, right? So that's all we're going to do here. So nabla dotted with nabla, okay, which equals nabla squared, is going to equal this whole thing dotted with itself. Okay. We're just gonna put a little dot there, right? But, okay, just to give you a better math background, we're going to basically FOIL this. So we're going to have this part, this x, this del per del x in the x hat direction, and then this partial part, right? So we're going to have a del per del x, x hat dotted with del per del x, x hat. But then we're also going to have this x, we're foiling, right? So first, outer, inner, last, that whole thing. And so then we're going to have this del x. We just did that one, but it's really multiplying by all of these, right? So because of this plus, so it's really multiplying by all of these. So now we're going to go with the y plus del per del x, x hat dotted with del per del y, y hat. Okay, here's the interesting thing. If you can recall from maybe linear algebra or calc 1, 2, 3, I don't remember which one we learned this in, but if you have this is an aside, x hat dotted with x hat, right? That's equal to 1. I'll explain why in a second. If you don't get that, don't worry. X hat dotted with y hat is equal to 0. Why? Basically, whenever we're dotting two vectors, right, because the hats are vectors, it's just of magnitude 1, we know that we're actually doing the projection. So we're saying how much of our x vector, our x hat vector, is in the direction of an x hat vector. What magnitude is there, right? Similarly, with this, we're saying how much of the x hat vector, that x position, x orientation, how much of that is actually in the y hat direction. And if you know your Cartesian coordinate system, right? You got x, y, z. These are all at 90 degree angles, right? There is no component of x in the y direction. Okay, so you know it should be 0, and 100% of the x hat is in the x hat direction, right? Because the magnitude of x hat, it's a unit vector, so the magnitude of it's 1. Another way to think about this, if that's a little confusing, is that you have the magnitude of x hat, which again it's 1 because it's a unit vector, times the magnitude of y hat, which is 1, it's a unit vector, cosine theta. That's what you do when you're doing the dot product, right? You can also represent it with trig as cosine theta. Now, question. The angle between x hat and y hat, what is it? It's 90. So, this is 90 degrees. What's the cosine of 90? Cosine of 90 is equal to 0. So this just whole thing becomes 0. So even though these are 1 and this is 1, we have a times 0, we get 0. So there's many different ways to prove this kind of stuff and to conceptualize it, but at the end of the day, the most important thing is that you know that if you have two orthonormal bases, meaning you have two vectors that are at 90 degrees to each other, if you do the dot product, you get 0. If you have ones that are along the same thing, you get 1, right? Whatever, and this is assuming their magnitude is 1. If their magnitude is different, you'll get slightly different numbers, right? Depending on that. So, how does this help us? We have an x hat, we have a y hat. They're being dotted together. Yeah, they have some like coefficients and stuff, but don't worry about those. Because x hat dot y hat equals 0. This whole thing goes away. This is very helpful because it makes the math so much easier. We now know that when we do this partial multiplied by that whole thing, the only component that is non-zero is the components in the same direction, right? So eventually these x hats are going to cancel and go to 1, but we'll save that for the next thing. So now that was the x hat direction. Let's do the y hat direction, right? Because we're foiling here. All right, so we have this y hat. It's going to multiply this whole thing. What's going to happen when we do it to this portion right here with the x hat? It's going to go to 0. What's going to happen when we do it to the z hat? It's going to go to 0. So really, we're only concerned about this. It's the only thing that doesn't zero out. So we're going to have plus del per del y hat dotted with del per del y hat, because it's the same thing. So that's nice. There's going to be some simple stuff after. We're going to change to blue. So z direction. We're really only concerned with this portion right here. But I'm going to draw showing that we're doing the whole thing, right? We're foiling. Super simple. Just algebra 1, basically. Del per del z. Z hat dotted with del per del z. Z hat. All right. So we got this big thing. All right. So what does this whole thing equal? Again, we're just solving. Super simple. Always keep in mind what we're solving for. We are trying to find what the Laplacian equals, what it means. So we can plug it back into our equation, our equation way earlier called Laplace's equation. If you've ever seen nabla, gradient squared, it's called the Laplacian. Okay. Now, this whole thing equals that squared. All right, let's solve. So, we have the derivative of a derivative. That's going to give us second derivative. We know what that looks like. We have x hat dotted with x hat. That's going to be 1. So we're going to have 1 times a derivative, second derivative. Boom, easy. It's going to be the same thing for all of these. If you look, these are all basically just changing the name of the variable. It's all going to be the same thing. So we're going to get nabla squared, or gradient squared, depending on what you want to call it. It's equal to, gonna do this in parentheses, del squared, right, because second derivative, just explain why, del x squared. And it's not going to be in the x hat direction, because like we said earlier, we have x hat dot x hat equals 1. Okay, so I just want to reiterate that the gradient squared has no direction. Okay, it's just a measure of the whole system, basically, or the whole whatever type of space you're looking at. Okay, so just want to make that extra clear. All right, plus del per del y squared. Oh, del squared per del y squared plus partial squared per partial z squared. Great, easy. Let's move on to plugging this in. So let's not get lost here. This was explaining what part of our original equation that we're trying to solve for is, right? So we have this part. Oh, whoa, that was weird. We have this part. And we have this. Okay, so let's plug it in. So again, we have, real quick, this squared on x of x, y of y, z of z equals 0. Okay, we're gonna have this whole thing, but now we're gonna plug. Boop. So we're gonna have, just gonna copy paste it because I am very lazy. Copy, paste. Great. So we're gonna have this acting on x of x, y of y, z of z is equal to 0. Okay, stop. Make sure we know what we got here. So we generalized our voltage, or our potential, depending on what you want to call it, and we expanded out our gradient squared. All right, here's where the interesting stuff happens. First, let me just make a minor adjustment. A lot of times we're going to call our x of x, we're going to call it big X, right? So just remember this is a function of x. We're going to call y of y big Y, okay? You're never going to guess what we're going to call z of z. Big Z. Great. All right. That is just to help with the writing because it's about to get pretty messy before it gets simplified. So I don't want to be writing x of x, y of y, z of z this whole time. In some books or some teachers, you'll see that this is actually, they'll call this instead, they'll call this v of x, right? X. Or this vy, right, etc. So just in case you see that, that's what they mean by this. It's the z, or it's the z component of your voltage, right? Okay. Sorry if this is getting discombobulating, moving around so much, but it's where it gets interesting. Let's, again, FOIL this out, right? So this is going to multiply by everything. We're going to have second derivative in the x direction of x, y, z, right? Plus second derivative of y, right? Or second partial y squared of x, y, z, right? It's not just going to be in the y direction. It's not just going to be in the x or z, but right now, foiling this out, plus second derivative with respect to z of the x, the y, the z. Please keep in mind that these x, this y, these z, this z, they're all functions. You cannot just say that because it's the second derivative of x that this goes to like 0 or something, because, well, if I take the first derivative with respect to x of x, that equals 1. No, because this isn't little x, this is big X. Okay, so this doesn't equal 1, this equals the whatever your chain is, right? So you'll have like partial x, and then you'll have a y and a z still. Okay, so that's just something to keep in mind for how partial derivatives work. This is a function, this is not a small variable. Great. So let's do this part first. I want to start by just showing you that this is actually del per del x of, so it's a derivative of a derivative, right? Acting on x, y, and z. Cool. So what does that go to? Again, I'm only doing the first part, so it's dot dot dot, right? Just to kind of isolate what we're doing here. So, inner part, inner bracket. That's going to be the derivative of your x function, okay, with respect to x. And now we know that the y and the z are both have nothing to do with x. So they're acting here as coefficients, because that's how partial derivatives work. So they're effectively just coefficients to this whole thing. So we can multiply now by a y and the z. Not a y, sorry, the y function, the z function. Okay, so this is what was in brackets. We're gonna have this del per del little x. Okay, let's do the other ones. So I forgot to set this whole thing equal to 0. So next part, let's do this. Right, so it's the same kind of thing. Oh, I guess we haven't finished, my bad. Technically I haven't finished yet. So what happens when you take the second derivative? So you already have this derivative here. You're gonna do another one, okay? Well, our y and our z functions are still independent, so they're not really going to be affected. They're just the coefficients, right? They have no change with respect to the derivative. So we're just going to get the second derivative of our big X times y times z. Okay, that's not that hard. That's pretty simple. So let's move on. Let's move on to this pinky part. Okay, so we're gonna have second derivative, and if we look at what we did earlier, we notice that it just becomes whatever respect we're doing with that function, right? Second derivative, and then the other things just become coefficients. So we can kind of just cheat a little bit, skip ahead, right? Understand that it's gonna be the same thing. So this whole thing is just gonna be the second derivative with respect to y of our big Y times X times Z. Again, functions, right? Functions of Y, functions of Z, functions of X, not just X, Y, Z, little variables. All right, let's do this one. We're gonna have plus second derivative of Z with respect to Z times our X function times our Y function. Okay, and then this whole thing equals 0. Whole thing equals 0. Okay, so let's copy that down a little bit neater. I'm just going to erase this part so we see what's happening. All right, so we're going to have second derivative with respect to x of our big X times our Y component times our Z component, right, of our potential, plus second derivative with respect to Y of our Y function times X times Z function plus second derivative with respect to Z of Z, right? X, Y equals 0. Okay, so all of this has been super simple. We haven't assumed any specific case. All of this has been general. So this is how physicists, how mathematicians end up going about solving for general solutions, and then eventually we're going to start making it more specific when we get to a practical example, such as the hot dog / gutter problem we discussed earlier. Okay. Now, where do we go from here? Well, this is the interesting thing. And this is where knowing that final solution of knowing the full path helps understand, where you're going. But there are times that we look at this and we go, how did they get there? A lot of people do trial and error. They kind of throw spaghetti at a wall, see what sticks. So I'm going to show you how they threw the spaghetti. Now, we are going to divide by this whole thing, both sides, right, by x, y, z, right, which is our potential. So let's do that. Divide by x, y, z. Divide by x, y, z, right? These are the functions, keep that in mind. Okay. So, bring up a new page. What's that gonna do for us? Well, we're gonna have del, or partial of x with respect to x. Now, on this first part, the y's, z's cancel out, right? And then we're just gonna have 1 over big X. So after doing this, it's like, oh, that makes so much sense. We wanted to show how we could write each of these components not with respect to each other, right? We don't want this X here and this Z here for our Y component. We want all of this stuff to be separate, hence the name separation of variables. So that's why we're dividing by this whole thing, by the X, by the Y, the Z, is that after doing it, it's like, oh, that makes perfect sense. Personally, I never would have thought of that, but it makes sense why we're doing it. Okay, so then we're gonna have a plus. Again, on this one, they're not gonna cancel out the same. They're just gonna leave a Y component, right? So we're gonna have the partial, second partial of Y with respect to Y. We're gonna have a 1 over Y here. Makes sense, cool. Plus second derivative. This is the Z function with respect to little boy Z. Kind of hard to tell the difference, but I draw them small so you can kind of navigate. 1 over big Z, all equal to 0. Okay, this is where separation of variables, we've checked the box, we've done it, we figured it out. Now comes the more conceptual part, sort of, or the more racking your brain for different answers part. But this is effectively, we've separated the variables, great. We're gonna take it and do some more complicated stuff to it, right? Now, I wanna know what this function possibly can be. What can this x of x be, right? What can this y of y be? What can all of these things be? And how we're gonna get there is, in my opinion, really cool. You know, or we know, that they all have to go to 0. So you could say, all right, well, x of x equals 0, y of y equals 0, 0, 0 equals 0. Kind of a cop-out answer, kind of a null solution. Doesn't really do anything for us. So what we're going to ask ourselves is, well, I know that, okay, let's call this constant A, right? Let's call this constant B. Let's call this part B. Let's call this part C. I know that A plus B plus C has to equal 0, right? So there has to be some combination of these three things that make them all cancel out. If not, right, like let's say our x, let's say we did this second derivative thing, we do the second derivative of x, and then we divide it by our original x, right? Our original function of whatever our v of x is. If we don't get a constant, then we cannot then add it to some other portion of what we get from our doing that to our y, and then some other portion of what we get to our z, and get 0. We would get something still dependent on our x, right? For instance, let's say I pick a random function, right? So again, we're kind of throwing spaghetti at a wall, seeing what sticks with our functions. Let's say I say my x of x is equal to x to the power of 7. Okay. Then if we do second derivative of x to the power of 7 with respect to, right? And then we do 1 over x to the 7. All I'm doing is plugging this in for our big X, right? If I do all this, then I will get, well, the second derivative is going to be, we're going to have 7x to the 6, right? Derived again. differentiate it again. So, right, we're gonna have that becomes 6 times 7, which is 42 x to the 5th, right? Over x to the 7th. This is gonna give us 42 over x squared, or you could write x to the negative 2, right? So this right here would be the answer for that. Just to show, again, this is the wrong answer, so don't go thinking that this is what we should do, just throwing absolutely random stuff, right? There's kind of a method to the madness later. Let's say y is the same thing. Let's say y of y equals y to the 7. Now, we know we cannot have x to the 7. Why not? Why can't we have that? Well, because the whole point was that this has to be a function of y. Not a function of x, not a function of z, it's a function of y. And that's what helps in the separation of variables of finding out what solutions can be, because again, we've been doing general solutions this whole time. We know that this still works even if this is a function of y. So we're going to say y 7. Okay. So again, we do this, y 7, we plug it into our formula. We're going to have y, so 1 over y to the 7, and we know that we're going to get the similar thing as we got here, right? So I'm just going to write that right there. Plus 42 y to the negative 2. Now, is there any way for us to add these two things together, for them to go to 0? And the answer is yes, right? Like if x and y equal each other. But again, they are variables. We can't just then pick an arbitrary location. This might be true in maybe a location, but not throughout all of the space that we're trying to identify. We're trying to get a general formula, and this general formula does not satisfy that then plus, again, there is a z part, but just imagine that there's not for a second, just for sake of argument, equals 0. This isn't always true. This whole thing's not always true, and we want something that's always true, not just true sometimes. So we know it can't be that, right? We cannot get something that gives us a rephrase. We cannot pick a function of x or pick a function of y that's going to pop something out that isn't a constant. When we do this, we have to get a constant. Let's just call it a, right? A constant meaning not dependent on the variable, or not a variable, right? We have to get something that's a constant. It can be b. We have to get something here that's a constant. Let's say c. Otherwise, when you add them together, they're not going to give you a 0 all the time. They're going to give you some weird wonky stuff if it's a variable. So now comes the interesting part. We have to figure out what function or what type of function can we do where this whole thing, right? You take the second derivative of your function. So what function? Or what type of function where you do this of f of x, right? Or f of y or f of c or whatever. And then you divide it by the original function equals a constant. Okay. I'm sure you can think of a few, right? Like if you have x, not x, sorry. There are really only, at least from what I've come across, 2 different types of functions that do that. Sinusoidal functions, right? So we're talking sine of x, right, or something, and cosine, right? Because they're both sinusoidal. And we also have exponential, which kind of makes sense, right? If sinusoidal is exponential, usually has similar stuff. So we're talking e to the power of negative x or e to the power of x. Right? Why is this important? Well, it helps us limit which functions we actually can have for our solutions. Super important. Because now we can kind of start to plug stuff in using these functions. Now, it's a lot of trial and error in order to get the right answer, and that's something that separation of variables is. It's trial and error. And you're going to try, and you're going to fail a lot. But you just got to keep plugging stuff in until it starts to work, and then we can relate the equations together. All right, let's do this. So let's say x of x equals, let's just say, now again, we want a general form of sinusoidals. So we don't want to leave out like what the coefficient is. Again, if I write like sine of x, I'm saying the coefficient right here is 1. We don't want that. That's not general. We need an a. We need some constant, some coefficient that we have there. So we have sine a sine of, and again, this x, got to put a coefficient there. Otherwise, it's not general. Otherwise, we're saying that the amplitude is 1. We don't want the amplitude of sine to be 1. We want it to be whatever function it could possibly be, right? We're trying to stay as general as possible here. Essentially, what we can have for our x of x and y and z of z is going to be dependent on those sine cosine functions or those exponential functions. And we want to keep it as general as possible so that we don't lose any solutions in our final result. So what we're going to do is our x of x, as you can see, is going to become x of x might equal a sine k of x, right? So we want to keep this k in there just as a generality for the actual angle of our function. And then it's going to be a plus, potentially a b cosine of k of x, right? Okay. And then what we could do is also say, or it could equal some variation of an exponent, so e, right? So we're going to have a, just some constant up front, times e to the power of k x, so we're going to stay with the same naming conventions, plus b e to the power of negative kx, right? And if you take the second, this notation is something, if you take the second derivative of this x function of either one, either the sine, cosine, or the e's, and then you divide it by the same function, you will get a constant, right? So these are the two types of functions that will do that. So now I'm going to save a little time, but we effectively do the same thing for our y's, that should be a z, our z of z, and we're going to have to put in a unique beginning term, right? Because they could potentially have like different constants, and we're going to have to put in a unique angled term, or the coefficient of the exponent, right? So again, that's just to stay as general as possible with our solutions because we don't want to miss out on the solution. All right. So what are we going to do from here? Now, what we can do is plug these 3 functions back into this whole equation and kind of see what works out, and maybe we can find that a certain variable might have to depend on like another variable, right? Okay, so we might find that like e is equal to a times c or something like that. All right, so let's do that with our x of x, right? You could do this kind of like by steps, and you'll start to notice a pattern. Okay, so x of x, what we're gonna do is del big X, del squared, over del little x squared. I've been forgetting this throughout the video, that's my bad. This little squared term. And then we're going to divide it by itself, right? By big X. All right. So when we do that with, let's start off with the a sine kx bit. What we're going to have is derivative of, I'm just going to do the derivative of this part in my head. So the first derivative would be, you'd have a times k, right, because chain rule, times the cosine of kx, right? So angle stays the same, and then it's going to be minus, because derivative of cosine is negative sine, so it's going to be minus bk sine of kx, right? Okay, so And then we're going to want to, again, divide this whole thing by this big part after we take the derivative. So that part has to go first. So now we're going to take the derivative again. And what we're going to get is we're going to have a negative a k squared, right? Again, because derivative of cosine is negative sine. Okay. Sine of kx. Okay, so chain rule, this came out. Right. And then we're going to have a minus again, right? Because derivative of sine is positive cosine, so the negative sticks. Plus, minus b k squared sine kx. Okay. And now what we're going to want to do is divide this whole thing by the original. Right. And again, the goal of this is to get a constant. So this whole thing divided by this part here, which is just going to be a sine kx, a sine of kx plus b cosine x. This should be a cosine. I did the derivative wrong. Alright, so what do we have here? What we could do is factor out a k squared and a negative k squared term from the whole thing, right? So then that gives us negative k squared right here times a sine of kx plus b cosine kx x all over a, it's kind of redundant here, but I just want to make sure that we all see what happens, plus b cosine of kx. Okay, so as you can see, numerator and denominator are the same, so we just get 1, right? So we have negative k squared times 1, or just negative k squared, right? So what we found here is this first part of the bigger equation. Right? But as you can see, we said earlier that our k, our q, our l, they're all constants. So we actually get a constant squared, which is really reassuring that we're doing something right, because we knew they had to become constants in order to eventually equal 0 when you add them all together. Okay, so we have that if x is equal to this thing, if our x of x function is equal to this thing, it'll spit out a k squared, a negative k squared, which is important, right? Because we know that some of the terms, if all of the terms are positive, you're going to get greater than 0. Okay, like if this term's positive, this term's positive, this term's positive, it won't equal 0. If they're all negative, it also won't equal 0. So what we need is for some of the terms to be positive, some of the terms to be negative. So now we're just hoping that for some of them we can, like if y is equal to this, and then z is equal to this, some of them will be positive, some will be negative, and then depending on that, you can kind of differentiate like how you should add them, or if you can all be sine cosine. Spoiler alert, they can't. So if x of x is this, then we get negative k squared. If x of x equals this, let's see what we get. And if we're hoping for a positive right now, because it means that this they're all the same formula pattern, just with different constant values. So we're hoping for a positive because that means we can add that positive and that negative together, get our 0. That's what we want. So x of x equaling a e to the kx plus b e to the negative kx. Okay. So derivative of x, I'm going to just do a little different route than I did here, just to be a little bit more explicit with respect to x, is equal to, well, this k is going to come out front, so we're going to have a k e to the kx, all right? And then we're going to have plus b, but then it's going to be a minus, right? Because this negative is part of the k, part of the coefficient for the x, so it's going to come up front. So we're going to have a negative b e to the negative kx. Okay. To the second derivative. So again, my notation's been sloppy throughout here, so I'm going to try to clean it up with how I do the... I've been missing this 2, I keep doing that, but equals, we're going to have a k come up front again, so ak squared e to the kx plus, right, because the negative again, b e to the negative, oh, you know what I forgot? I forgot that this k come out front there. My bad. Kx, okay, k squared e to the negative kx. Great. All right, so now what do we need to do? We need to divide this whole thing, right? Because, okay, going back to our formula, this is what we're doing. So now we need to divide by that 1 over x. So then this whole thing over x, so I'm going to write that explicitly here, of x over this partial, so second derivative over x of x, right? And this equals a k squared e kx plus, right, this is super important, the plus sign, plus b k squared e to the negative kx. So a lot of this stuff, I mean, you're using differential equations, but really it's algebra. All right, so now we're going to have an a e to the kx plus, this is our original x of x in the denominator here, bk squared, not k squared, my bad, b e to the negative kx. Boom. All right, so what we notice here is that, again, we can factor out a k squared term, and this equals k squared, and then times, you can pretty clearly see that this would just be this over itself, right? So times 1, which just gives k squared. So what we have here is that we have the ability to use the sine cosine variance to get a constant of negative k squared, right? So whatever that angle portion is. And then we also have the ability to use the e's, right? The Euler constant, to get the same thing but positive. Now, do keep in mind your k value may or may not equal your q value, may or may not equal your L value, right? So like those angles that we have for different x, y, and z. But you can create a relation with them depending on what the conditions of the problem are. Meaning, there are times when you'll have a problem that gives you a electrically charged box, or electrically charged, sometimes they call it a gutter, right? So it's like a rectangular prism with the two top and bottom faces taken off and maybe like the top panel. And what you can do is realize that, I'm going to kind of give an example here. All right, so you might have this sort of like rectangle, and they're like, oh, all this dashed lines means that it's electrically charged there. But at this wall right here, this face, it's a constant form of like potential or something, right? And then at this other face, it's also a constant potential. And what you can see here is that as you move along this x direction, right? So we're going to say x is to the right and left, right? As you move along this direction, you're going to go from a certain constant, like v naught, and you're going to meet again at v naught. What does that look like? That kind of looks like you could do that, do sinusoids, right? So you can kind of guess and check which ones would work. And you can get a knack for it. If you can't get it immediately, what you could do is just plug and chug, and really just put in like what if x is e to the x, right? And then what if y, and do all of the different permutations of these, right? So you have 3 slots, and each is 2, right? So you have quite a few permutations, but it's manageable enough to do. So what you could then set out of, let's say you did all your boundary conditions, and you realize that you need like your x to be the sine, your y to be the e, and then a z to also be a sine, right? What you could have is this function of, that your z in this equation, right? This is going to become, as we proved here with the x's, it's going to be the same thing, but with your L, right? So if z is the sinusoidal, right? Then you know that it's going to give negative L squared when you do this whole operation, right? This whole thing. And then you know that your y, let's say, I think I said it was the exponents. Let's say it's exponential, like so e to the qy variant, right? That it's going to give you your q squared. Okay. And then for the x one, let's say it's also sinusoidal. Then you're going to get out of this whole thing, you're going to get a negative k squared, which we just solved. Now, sometimes also you can recognize that like a b term might not be applicable, or a d term, but that's up to the exact problem and example. So I think that's effectively covered everything for separation of variables as far as just the math side goes. And then once you start doing physics problems, that's where the actual thinking and plugging in at different boundary conditions and stuff comes in as well. But I think this has been a long enough video for that. So just to reiterate, your x, your y, your z, after you separate it, can become any of these functions, right? And again, these are all general. The e is a constant, L, q, k, a, c, all of those are constants. You have to, if one of them, in order to satisfy this equation equaling 0, if one of them is a sinusoid, then the other one's going to have to be an exponential. And then the third one can be either, right, depending on whatever you want to set these constants to. So it's very general, so it's manipulated. You can manipulate it for your problem, but that's all for today.